Now let us derive the three-dimensional green function by using the Fourier transform. We start from the green function equation for the three-dimensional Helmholtz equation. We apply the three-dimensional Fourier transform with respect to the spatial coordinates. Using the Fourier transform of the partial derivative with respect to x, we have minus jk sub x times g tilde. In the same way, the Laplacian term is transformed into minus kx squared, minus ky squared, and minus kz squared, multiplied by the transformed green function. The second term, k squared times g, remains k squared times g tilde in Fourier space. On the right-hand side, the Fourier transform of the delta function becomes minus 1. Therefore, in Fourier space, the green function is obtained in this algebraic form. Next, we perform the inverse Fourier transform in order to recover the green function in real space. To evaluate the inverse transform, we introduce spherical coordinates in k space. Let the magnitude of the wave number vector be k prime. Let theta sub k be the angle between k and r, and let phi sub k be the azimuthal angle in the plane perpendicular to r. Then the volume element is written in spherical coordinates in k space. Therefore, the inverse transform can be converted into an integral in spherical coordinates. Since the integrand does not depend on phi sub k, that integration simply gives a factor of 2 pi. Next, we integrate with respect to theta sub k. Let us change the variable of theta sub k to t, where t equals minus cosine theta sub k. In this case, dt is given by this expression, and the integral becomes elementary, and we obtain two terms containing exponential of plus jk prime r and exponential of minus jk prime r. Now consider the final integration. In the first term, we change the variable from k prime to minus k prime. Then the two terms combine into single integral from minus infinity to infinity. This is now suitable for contour integration. To choose the contour, we regard k prime as a complex variable. The exponential factor contains exponential of minus j k prime r. If the imaginary part of k prime is negative, then this factor decays exponentially for positive r. Therefore, we close the contour in the lower half plane. Their integrand has poles at plus k and minus k. With the small loss interpretation, the pole at minus k is avoided just below the real axis, and the pole at plus k is avoided just above the real axis. So the contour encloses only the pole at plus k. Therefore, by the residue theorem, we evaluate the integral from the residue at k prime equals k. This gives the final result. The green function in 3 dimensions is exponential of minus jkr divided by 4 pi r. Thus, by using the Fourier transform and contour integration, we obtain the same green function as before.